Think of a great all-purpose outfit, something you might reach for in the closet if you don't know what the day is going to bring, something that will serve most purposes well. Maybe you reach for something like this, a light jacket and some matching shoes. This guy is prepared for a lot of kinds of days, but not every kind of day. If you're going to a job interview, he might want to at least add pants. Similarly, when we spend a bunch of time building our predictive models on our data, we reach for an off-the-shelf evaluation metric, something like accuracy. And in this talk, I'm going to try to convince you that you should probably put that back on the shelf and go for something custom. There's a lot of value to be gained there. When I was a freshman in college, I lived in a 7-story dorm with hundreds of other young men on their own for the first time. What could go wrong? A lot went wrong. One of those things was a fire alarm that went off many, many nights and sometimes many times during the night, usually the night before midterms or final exams or when projects were due. And we figured out people would stay up late making popcorn in their microwaves, burning the popcorn, and the fire alarm hated that smell. And so it would go off all the time. We would file out of the dorm, all 7 stories, all hundreds of freshmen, and the fire department would have to be called in to go room by room and clear it before they let us back in. Now, this fire alarm was very sensitive, I thought it was much too sensitive. In fact, I was losing a lot of sleep, and my academic performance probably went down because of that fire alarm. I moved off sophomore year, lived in an apartment after that. However, years later, I realized the fire alarm was probably tuned right, because even though a lot of people lost a lot of sleep and their grades suffered, if it had made the other kind of error, not going off when it should have gone off, the cost would have been incalculable. So thank you, fire alarm. And similarly, if we were to try to connect this idea to a business use case, say developing a fraud model at a bank where we look at transactions that customers submit and try to label them as benign or potentially fraudulent, the same phenomena occurs where one kind of mistake is much, much more costly than the other. So if we flagged a transaction that should not have been flagged, a benign transaction gets halted and the customer gets locked out of their account. That's annoying to the customer. It costs them time, and it costs us at the bank time as well. But letting a fraudster get a hold of a customer's account damages the company's reputation and can potentially cause a much larger issue for the customer. And so fraud is much more of a problem, dollar-wise per transaction, than flagging a benign transaction. So if we were to build a binary model, meaning a model that predicts 0 or 1, in this case, not fraud or fraud, the model will go through all the cases that it sees, every transaction, and give it a probability between 0 and 1 of fraud. And the default to do in that case, if you're trying to decide on how to use that probability to predict the event, is to take the default threshold of 0.5. If a transaction is more likely, means there's more than a 50% chance that it's fraud, to be fraud, then we say it's fraud. And if it's less than a 50% chance of being fraud, then we say it's not fraud. However, there are a couple problems with this approach. One is that a model that's trained on a large data set consisting of mostly non-fraudulent transactions will struggle to get even a single record predicted as more than 0.5% or more than 0.5 chance of fraud. And so this threshold might not even come into play at all in your decision making. The other problem is one we've already talked about, that this kind of error here, freezing a benign transaction, costs a lot different amount of money than letting through a fraudulent transaction. And so we need to take that into account. What we'll do is we will simulate what would happen to the business if we used the threshold between 0 and 1. Go ahead and use 10 or even 100 different thresholds within that range. Count up the number of times it will cause you to make this mistake and multiply it by the cost of making that mistake. Do the same with this kind of mistake and the costs associated with it. If we set the threshold very low, in this example, it means that almost all transactions are going to be flagged as potentially fraudulent. We're going to make many, many of these kinds of errors, many, many small errors. And then on the other extreme, if we set our threshold very, very high, it means almost no records are going to be flagged as fraud. We're going to start letting in some of these really large errors. And so somewhere in the middle, you're going to find that there's a region where the total cost is minimized. So you might say anywhere in here, we're okay with the total costs of making the kinds of errors that we're seeing here. You would choose a region in between those 2 points that is agreeable and acceptable for your business, depending on what else you might want to prioritize. You would try to minimize the overall costs in that way. And so that's probably going to look a lot different than just going with point 0.5. And it requires some business knowledge and actually contextualizing your model within the parameters of what it's actually going to be affecting. So we believe that if you've gone to a lot of trouble to specify a model carefully, to train it and test it, make sure your data is clean and represents reality, then don't forget the last step of customizing and contextualizing the way that you're actually evaluating that model's performance. Make sure that it's helping you make a decision that's actually grounded in the reality of what you're applying it to.